This is the lecture over section 28.3. We're going to be looking at the nuclear atom and the Bohr model. So in the Bohr model of the hydrogen atom, the allowed values of angular momentum for an electron in a circular orbit are integer multiples of the constant h divided by 2 pi. So you can see how they come around there. Now, remember, angular momentum, that's something that certainly we would think in a planetary model would cause, eventually you would see a degradation, just simply because you have some sort of force that would be acting on it that might be slowing the angular momentum of the electron. But that's not something that we actually see. So that we're going to have to get used to looking at angular momentum a little bit differently here at the atomic level. The integer n is called the principal quantum number. It also determines the electron's radius and the orbital speed for each level. So you can see the radius for that particular energy level, and you can also see the orbital speed for that. And we'll get to this picture here in just a little bit. It's a little clue as far as how it's structured. So, how do you know what the inside of an atom actually looks like? I mean, you've got concepts out there that have been handed to you, but how do you know? We know that atoms are much smaller than the wavelengths of visible light, so you really can't go into it and look at it. But how do we describe it? Well, J.J. Thomson, back in good old 1910, had discovered that the electron and started measuring its charge-to-mass ratio in 1897. And also by 1910, Millikan had completed his first measurements of the electron charge. So these and other experiments showed that most of the mass of the atom had to be associated with a positive charge and not with the electrons. It was also known that the overall size of the atom was on the order of 10 to the minus 10 meters, and that all atoms except for hydrogen contain more than one electron. What they didn't know was how the mass and the charge are distributed in the atom. You know that all of this other stuff is going on, you know these properties, but still, how's this thing put together? So Thomson had proposed a model of the atom that included a sphere of positive charge on the order of 10 to the minus 10 meters in diameter, with the electrons embedded in it like chocolate chips in a more or less spherical cookie. Something like that. So the first experiments designed to probe the inner structure of the atom were the Rutherford scattering experiments. These are carried out in 1910, 1911 by Sir Ernest Rutherford and two of his students, Hans Geiger and Ernest Marsden, at Cambridge. Rutherford's experiment consisted of projecting alpha particles emitted with speeds on the order of 10 to the 7th meters per second from naturally radioactive elements at the atoms under study. The deflections of these particles provided information about the internal structure and charge distribution of the atoms. And alpha particles are now known to be identical to the nucleus of helium atoms. So Rutherford's experimental setup is shown here. Radioactive material right here emits alpha particles. This thick lead screen stops all the particles except those in a narrow beam defined by small holes. So in other words, this is going to stop everything except those going straight at a trajectory here of a gold foil onto that gold foil target. And gold was used because you can take gold and beat it into extremely thin sheets. After passing through the foil, the beam strikes a screen coated with zinc sulfide, similar in principle to the screen of an older model TV picture tube. Momentary flash or scintillation can be seen on the screen whenever it is struck by an alpha particle. Just as spots on TV screens glow when the electron beam strikes them. Rutherford students were assigned the tedious task of counting the number of particles deflected through various angles. And again, as a graduate student, you get stuck doing a lot of things that the professor overseeing it doesn't want to do. And so Geiger is the guy that got to go through this, and he led or invented something that's now called the Geiger counter, radioactive detector. The fact that the alpha particles can pass through a thin metal foil shows that alpha particles must be able to actually penetrate into the interiors of the atoms. The mass of an alpha particle is about 7,300 times that of an electron. So momentum considerations show that the alpha particle can be scattered only a small amount by its interaction with much lighter electrons. In other words, it's like driving a car through a hailstorm. The hailstones don't deflect the car much. And that's effectively what you're looking at as far as the helium atom is concerned. Only interactions with positive charge, which is tied to most of the mass of the atom, can deflect the alpha particle appreciably, perhaps comparably to colliding with the oncoming truck, which if you're doing that in a hailstorm, you've got some real bad luck. So in the Thomson model, the positive charge is distributed throughout the whole atom. Rutherford calculated that the maximum deflection angle of an alpha particle that you would have here is only a few degrees. Obviously, if you're only having a little bit of interaction with some of the positive charge, even if it is more massive than the electron charge, you're still not going to get that much deflection. However, the experimental results were very different. Some of the alpha particles basically came in and got shot straight back. That basically was a pretty incredible find. It's almost as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. This is what was going on. You could see some really rather large deflections. Only way you're going to be, you can't have that really going on with this model. That model of the atom is not going to work. If, however, everything is concentrated at the center, you can get that kind of result. And that's the experiment. That's what he was trying. That's what the experiment showed him, is that this is the only way that you're going to be able to have results like that. And that's what this paragraph here is going to be discussing. So he computed the numbers of the particles expected to be scattered to various angles within the precision of his experiments. The computed and measured results agreed down to distances on the order of 10 to the minus 14 meters. So his experiments established the atom does have a nucleus, a very small, dense structure, no larger than 10 to the minus 14. The nucleus occupies only about 10 to the minus 12th of the total volume of the atom, but it contains all of the positive charge and almost all of the mass of the atom. So this is a computer simulation of the paths of 5 MeV alpha particles scattered by the gold nucleus within a radius of 7 times 10 to the minus 15 meters, and by a nucleus with hypothetical radius 10 times this rate. So in the second case, there is no large angle scattering because the nucleus is diffuse. So at the same time that Bohr established a relationship between spectral wavelengths and energy levels, he also proposed a mechanical model of the hydrogen atom. And using this model, now known as the Bohr model, he was able to calculate the energy levels and obtain agreement with values determined from spectra. So looking at Rutherford's discovery of the nucleus, the question arose as to what kept the negatively charged electrons at relatively large distance from the extremely small positively charged nucleus, despite the electrostatic attraction that you would think a positive and negative charge would pull together and annihilate. Rutherford suggested that perhaps the electrons revolve in orbits around the nucleus, just as planets revolve around the sun, with an electrical attraction of the nucleus providing necessary centripetal force. But if you start looking at classical electromagnetic theory, any accelerating electric charge, either oscillating or revolving, radiates electromagnetic waves. just like you have with radio or TV transmitting antenna. Total energy of a revolving electron should therefore decrease continuously, and its orbit should become smaller and smaller, and eventually spiral into the nucleus. And then, according to classical theory, the frequency of the electromagnetic waves emitted should equal the frequency of the revolution of the electron's orbits. As the electrons radiated energy, their angular velocities would change continuously, and they would emit a continuous spectrum, not the line spectrum that you actually see. So, of course, not wanting to watch classical electromagnetic theory fall apart, we, of course, have to think on the fly and try to figure out why this is not the case. So Bohr postulated that an electron in an atom can revolve in certain stable orbits. In other words, I'm making this stuff up as they go along, with the definite energy associated with each orbit without emitting radiation, contrary to predictions of classical electromagnetic theory. So according to Bohr, an atom emits or absorbs radiation only when it makes a transition from one of these stable orbits to another, at the same time emitting a photon with appropriate energy. To determine the radii of the permitted orbits, Bohr made what we have to regard in hindsight as a brilliant intuitive guess. He postulated that the angular momentum of the orbiting electron is quantized. So in other words, it's only got specific values, it's not a continuous spectrum. Specifically, Bohr proposed that the angular momentum must be an integer multiple of Planck's constant divided by 2 pi. Note that the units of Planck's constant h, usually written as joules seconds, are the same units of angular momentum, usually written like this. Bohr postulated that in the hydrogen atom, only those orbits are permitted for which angular momentum is an integer multiple of this. Angular momentum of a particle of mass m moving at speed v in a circle of radius r is going to be this. You can go back to chapter 10. So Bohr's assumption looks like this. So if you consider a mechanical model of the hydrogen atom that incorporates this equation, the atom consists of a single electron with mass m and charge minus e revolving around a single proton. The proton is nearly 2,000 times as massive as the electron, so we'll assume the proton does not move. We learn in chapter 6 that when a particle with mass m of this speed in a circular orbit with radius n, its acceleration has a magnitude of this. According to Newton's second law, force with magnitude of this is needed to cause this acceleration. So the force is provided by the electrical attraction between the two charges. And according to Coulomb's law, we can then write all of this. K, remember, is 1 over 4 pi e naught. Using this force in Newton's second law, we come up with this is equal to this. So you combine those equations, basically you can find the radius with the quantum number, and you can also find the speed. So the minimum Bohr radius ends up being this, and it gives us a pretty good estimate of the size of the hydrogen atom, which is in its lowest energy state. And that's where we come up with this equation, this basically being R1 being the minimum radius here. You can use these equations to find the kinetic and potential energies for an electron in an orbit with a quantum number n. When you do that, you can come up with these equations. We're not going to focus too much on how we get there. These are the Bohr model energy levels that are produced for these particular energies. And we can also see the relationship of the Rydberg constant to certain other fundamental concepts as well. So, although the Bohr model predicts the energy levels of the hydrogen atom correctly, it raises many questions. It combines elements of classical physics with new postulates that, hey, we don't have any real basis for it except that they just work. There's no clear justification for it, except that it just leads to the right answer. The model proposed or provided no insight as to what, basically, why is this happening? We don't know. The stability of certain orbits was achieved at the expense of discarding the only picture available in Bohr's time of the electromagnetic mechanism by which the atom irradiated energy. The angular velocities of the electron motion were not the same as the angular frequency of the emitted radiation, a result that is contrary to classical electrodynamics, and the attempts to extend the model to atoms with 2 or more electrons were not successful. So we'll have to wait till chapter 29 to figure out exactly what we're going to do about that.